Applications of determinants and matrices. In this module, you will learn about applications of determinants and matrices. To know the applications of determinants and matrices, we will consider a system of linear equations in 2 or 3 variables. A system of linear equations in 2 variables. These linear equations in 2 variables are in pairs. They are of the type a1x plus b1y equals c1 and a2x plus b2y equals c2. For example, consider the following pair of equations. 2x plus 5y equals 1 and 3x plus 2y equals 7. Let the system be written as ax equals b. Let us find the value of determinant a. The value of determinant a is 0. The value of the determinant a is not 0. This implies that a is a singular matrix. This implies that a is a non-singular matrix. Next, we calculate the product of the joint a and b. Next, we calculate the inverse of a as a joint a by determinant a. If the product is 0, then either infinite solutions or no solution will exist. If the product is not 0, then no solution will exist. Now multiply both sides of the equation ax equals b by a inverse. Then x can be calculated as a inverse b. A system of equations is said to be consistent if its solution exists. A system of equations is said to be inconsistent if its solution does not exist. We restrict ourselves to a system of linear equations having unique solutions. Consider the equations. 2x plus 5y equals 1 and 3x plus 2y equals 7. In matrix form, it can be written as ax equals b, where A is a 2 cross 2 matrix with the elements 2, 5, 3 and 2, x as a column matrix of unknowns x, y and b as a column matrix with the elements 1, 7. Here, determinant a equals minus 11 implies that determinant a is not 0. We next calculate a joint a. A joint A is a matrix, the elements of which are 2, minus 5, minus 3 and 2. When a joint A is divided by determinant A, we get A inverse. When A inverse is multiplied by matrix B, we get a column matrix with the elements 3 and minus 1. X, the unknown matrix with the elements x, y, equals 3 and minus 1. This implies that x equals 3 and y equals minus 1. Next, we will consider a system of linear equations in three variables. They are of the type a1x plus b1y plus c1z equals d1 and a2x plus b2y plus c2z equals d2 and a3x plus b3y plus c3z equals d3. For example, x minus y plus z equals 4, 2x plus y minus 3z equals 0, and x plus y plus z equals 2. In matrix form, it can be written as AX equals B, where A is A3 cross 3 matrix with the elements 1, minus 1, 1, 2, 1, minus 3, 1, 1 and 1, X as a column matrix of unknowns X, Y, Z, and B as a column matrix with the elements 4, 0, 2. Here, determinant A equals 10 implies that determinant A is not 0. We next calculate the cofactors of matrix A, which are given by 4, minus 5, 1, 2, 0, minus 2, 2, 5 and 3. We next calculate adjoint A, which is a matrix given by 4, 2, 2, minus 5, 0, 5, 1, minus 2 and 3. When adjoint A is divided by determinant A, we get A inverse. When A inverse is multiplied by matrix B, we get a column matrix with the elements 2, minus 1 and 1. X equals the column matrix with the elements 2, minus 1 and 1. Hence X equals 2, Y equals minus 1 and Z equals 1. In this module, you have learned a unique solution exists if determinant A is not equal to 0. An inverse can be calculated as adjoint A. By determinant A, the unique solution for Ax equals B is given by x equals A inverse B. A system of equations is said to be consistent if its solution exists. A system of equations is said to be inconsistent if its solutions do not exist.